The next type of source that has planar symmetry that we'd like to look at is a slab of charge. Now this is an semi-infinite slab of charge. I'll write down x equals 0 here in the middle, and this side is x minus d over 2, and we'll call this x d over 2. So the slab has size d. And this slab has a charge density rho, and for this particular example, we're going to consider the case where rho is uniform, and we'll make it positive. Now, just like because a slab has the same planar symmetry as a sheet, we know that the electric field will point away from the slab, and we actually have 4 regions here. 1, 2, 3, 4. And on the outside, I'll just put E outside with the region denoted. The field should point away. Now inside, it's interesting that we know at the center, the field has to be 0. Now why is that? Because if the field is pointing away, somewhere in the middle, it has to be 0. And by the symmetry, it has to be at the center of the slab. And that will tell us that on this side of the center, E3, the field is going to be pointing to the right. And on this side, E2, the field will be pointing that way. And that is what the electric field looks like inside the slab. And now, to make this calculation, we have to choose some Gaussian surfaces. And there's a lot of different ways to do this. So we'll begin by looking at regions 1 and 4. And we're going to choose a Gaussian surface and again exploit some symmetry. So let's draw the slab. It's a thickness d, a charge density rho. And if we pick equidistant s on both sides, we expect the fields to have the same magnitude by symmetry. So our Gaussian surface will look like a cylinder. And the charge enclosed is in this region. Now again, we have n hat, this is region 4. We have n hat, region 1. We have E, region 1. We have E, region 4. But we've said those are the same magnitudes. So we can apply Gauss's law that the flux of E is equal to the charge enclosed. And now, once again, we can calculate. Because the electric field points away, there's no flux through the body of the cylinder. And we have just flux on both sides. E is pointing out on both sides. So that flux on both sides is positive. And we'll write it as just E1. And we know in magnitude that E1 is equal to E4 in magnitude. So I'm going to write that as E1 times A. I'll write another E1 times A, because they're the same magnitudes. And the charge enclosed, now this is a volume charge density. Rho is charge per volume. So what is the volume of a cylinder? Well, it's just the cross-sectional area A times the thickness of the cylinder, D, and we divide by epsilon naught. And so we get 2E1A by applying Gauss's law, rho A d epsilon A, and the magnitude of the field is given by rho d over 2 epsilon naught. Now, remember, it's pointing, let's call this our positive I hat direction. In region 1, it's in the negative I hat direction. And in region 4, it's in the positive I hat direction. Now, what about inside? Well, that's a little bit trickier. And what we'd like to do is now draw another Gaussian surface for the region inside. And I'll try to show that over here. So inside, I'll draw my slab. And now I could do the same type of symmetric Gaussian surface as I did before. But I'll make it inside the slab. And I have E2, E3, pointing out, and I'm going to call this my variable x. So my Gaussian surface is probing the inner region where x can go from 0 to some distance out here, but the whole size here, let's make x positive in this case, is just 2x. And now by symmetry again, our Gaussian law calculation, flux of E equals charge enclosed over epsilon naught. Well, the flux is still one side over here plus one over there. We still have a cross-sectional area A. So I get 2E, and I'll just call it doesn't matter. They have the same magnitudes. I'll call this time magnitude 3A equals the charge enclosed, shade in that charge enclosed, and we get rho times the size, 2x, times A over epsilon naught. And this tells us that our electric field is E3 is equal to rho x A's cancel on both sides. So we get rho x over epsilon naught. And that is our electric field in regions 3. It points this way. The magnitude in region 2 is the other way. And we want to finish by writing down an expression for all of the electric fields in these regions. And I'm just going to give myself a little space over here. And this is a little complicated, but we'll write E. So in region 1, which is when x is less than minus d over 2, we calculated that field, rho d over 2 epsilon naught in the minus I hat direction. Now, I can do something interesting, which you'll see handles both cases. Inside the slab, I'm going to write my electric field as rho x over epsilon naught I hat. And you may think that, wait a second, it's pointing in a different direction for negative x over here. But the direction here is when x is negative, it's in the negative I hat direction. And that's precisely the way the field points. When we're on the positive side and x is positive, it's pointing in the positive I hat direction. So this expression handles the field in that region. And finally, we have rho d over 2 epsilon naught I hat when x is bigger than d over 2. Now, again, what about at the boundaries of the slab? Well, if we made these results all equal, you can see that when you set x equal to d over 2, our fields will be continuous. And so our results extend like that. And that's how we describe the electric field in all 3 regions of space. This is a detailed calculation and a little bit long to do, but there we have it for the infinite slab.